These are the slides to accompany Chapter 24 on spectroscopy and the lab on spectroscopic analysis of iron by UV analysis. In order for us to understand the spectroscopy well, though, we really need to understand light, since spectroscopy is really the measure of the interactions of light with matter. Light's made up of both waves and particles. The waves are electric and magnetic. There's components of each, and those wave and electric components allow us to interact with matter. And then we also have photons, and we'll talk about those a little bit later. So anytime we have a wave, we have a few different factors that are important. One is the period, and another is the frequency. Now, when we're talking about waves of length, we'll oftentimes talk about the frequency as the Greek letter nu. I always use F instead because nu looks an awful lot like V and it gets confusing. So I will be using F instead of nu. And the units of frequency are always hertz or some metric prefix along with hertz. Hertz really just means inverse seconds, 1 over seconds. So if we're talking about waves per second, we give it a unit of per seconds. We also can talk about wave number, which is another measure of frequency. Wave number is going to be given the variable nu with a bar above it, nu bar, and it gives units of inverse centimeters. So really what is meant by wave number is the number of waves that pass through in any given centimeter, and you can actually convert that by using the speed of light and the frequency, or the speed of light and the wavelength, but it's kind of a pain to do that. Some people will use wave number and will particularly use wave number in infrared spectroscopy. Wavelength is another factor. Wavelength is essentially the same as the period of a wave. When we use light, we talk about wavelength with the variable lambda, and we give it units with m as a base, m being meters. Of course, we could use different metric prefixes because the types of wavelengths that we cover with light are broadly different. So visible light, we usually use nanometers. If we're talking infrared light, then generally we're talking in the micrometer range. We also talk about velocity. Velocity then would be equal to, velocity equals the frequency times the wavelength. If our frequency has units of 1 over seconds, and our wavelength has units of meters, we can see that we'd end up with a velocity in meters per second. So the speed of light is always given the variable c, that's the velocity of light in a vacuum, is 2.998 times 10 to the 8th meters per second. Now that's in a vacuum. It's very close to that when it's in air as well, and so we usually use that speed of light for air. We know that light also has properties as a particle because we know that light gives energy in discrete packets. So whenever we absorb energy into a molecule or an atom, we end up generating discrete bands of absorption that allow us to indicate what types of photons are actually being absorbed. So the energy that's given by each of those discrete bands is going to be given by a constant called Planck's constant, h, we can look that up pretty much anywhere, I'm not going to repeat it here, times frequency. Now that means that it's also going to be equal to h times the speed of light divided by lambda, since we know that frequency times lambda equals the speed of light. So we could use either wavelength and the speed of light, or we can use frequency to determine the relationship with energy. Notice that then frequency is directly related to energy. The higher the frequency, the higher the energy, whereas wavelength is indirectly related to energy. So the longer the wavelength, the lower the energy. So if we have light in different colors, we can actually tell based on the wavelength how much energy is with this light. We have, again, the delta E's that we're going to observe are going to be the energy of light that's absorbed or emitted. That only happens in discrete levels because energy is delivered by light in photons, in packets of energy. And it only is allowed in discrete packets because we have different energy states for each of our electrons in our molecules. So if we use this relationship that we just defined for energy and frequency, or energy and wavelength, and we look at this scale, this visible spectrum, we see that red light is around 700 nanometers, and we see that violet light is around 400 nanometers. So using that information, can we tell whether the flash or Savitar actually has higher energy? We should be able to see very clearly that the flash actually has lower energy because he's red and has a longer wavelength, and Savitar, being blue, has higher energy, which is maybe why they are such formidable opponents. We also know that the type of energy that's released by light is going to determine the types of interactions. So if we have very, very high frequency, we're going to actually be able to change nuclear configuration. This is what happens in gamma rays. Gamma rays are very high frequency and therefore very high energy. Remember, frequency and energy are directly related. We're going to actually be able to change nuclear configuration. So we can essentially move the identity of a nucleus around by putting a ton of energy into it. We can cause nucleuses to split. We can do all sorts of really interesting things that we don't really do a whole lot in our labs, but are related to spectroscopy. We can also look at X-rays, which are lower frequency. They're going to change electron distribution, but they're not actually going to change the nuclear configuration. So X-rays are going to move things from inner shells to outer shells. They can tell us a lot about the shape of solids. They can also tell us a lot about the types of metals that are in certain things, and they can be a really powerful technique to use. Visible and ultraviolet light can tell us what's happening, not going from inner core electrons to outer, but just from the valence electron changes. So we see things moving from the outer valence shell up into a higher energy level. So that's going to tell us a lot about organic molecules, a lot about metals and how those are interacting with ligands, and that can be a really valuable thing for a lot of really simple analysis that we'll talk about later in this chapter, and frankly what we did in lab as well. We can also use infrared spectroscopy. It's going to change the configuration of a molecule. It's going to cause it to vibrate or bend or wiggle. So we'll see a bunch of different movement related changes. And those can be really helpful for telling what types of functional groups are in a molecule, or how a molecule is shaped, and that can be a really helpful thing too. Microwave is going to be really good for changing orientation of a molecule. So we use it in labs sometimes to excite molecules. We don't use it as often analytically. We can also have electron spin repulsion, which is now a lower energy. We're essentially just giving enough energy to change the spin of electrons. So we're moving from one direction spin to another direction spin in electron spin repulsion. And we also can do nuclear magnetic resonance, where we change the spin of a nucleus. That only works with nucleuses that have spin, but protons have spin, and so that's one of the most common things that we do for analysis of organic molecules that have lots of hydrogens in them and lots of carbons in them. Carbon-13 also has spin that we can measure this way. So essentially we're seeing that depending on the type of energy we put in, we can get different information about the molecule. We also can think about the types of transitions that are possible, particularly in UV vis, in order to determine what types of analysis we can do. So we can do absorption spectroscopy. Absorption spectroscopy is one of the most common forms of spectroscopy, and it's really helpful for determining concentrations of unknowns. It's a very, very common thing to do colorimetric methods on, and that's what we did in lab for this section. And then we can also do emission spectroscopy. Emission spectroscopy includes things like chemiluminescence. That's like glow sticks, right? So you have a chemical reaction that causes things to brighten up. That also includes bioluminescence. Most bioluminescence is a chemiluminescence, so fireflies or glowing jellyfish would be considered a bioluminescence. We can also have fluorescence. Fluorescence is going to be when we are using energy of one wavelength to excite something, and then when it relaxes back with a different energy. And so when it relaxes back and emits, it's going to give off a different color, and that would be fluorescence. Phosphorescence is another type of emission spectroscopy, but it's a little bit more difficult to understand what's going on. So whenever we are doing fluorescence, fluorescence involves the excitation at one wavelength, and then a relaxation, back down like this, and then after a relaxation, it's usually vibrational, then we have an emission that's at a different wavelength, usually a longer wavelength and therefore less energy. So the fluorescence is because it only is a relaxation by vibration, allows us to generate the fluorescence on the order of 10 to the minus 8 to 10 to the minus 4 seconds, so pretty quick after we have the initial excitation. Phosphorescence is like when you have glow-in-the-dark things. Glow-in-the-dark things oftentimes have a much longer time scale, and that time scale is because we're going to excite right away. After we excite, we're going to end up having some sort of intersystems crossing where we move from a singlet to a triplet state, which means we're flipping spins. Then we have a relaxation within the triplet state, and then we cross back into the singlet state and have another relaxation. It's that second relaxation that we see, but because we have so many different changes in energy, it takes a little while to do that, which is why phosphorescence is a longer time scale. All of our emission spectroscopy goes linear with concentration, so it's really nice to measure concentrations analytically, but not everything will do these types of emission spectra as readily as we can find absorption spectra. So that's where we're going to focus our talk. So absorption spectroscopy is a fairly simple form of spectroscopy where we start with some sort of light source. We're going to have some intensity of light that's coming off of it. It's going to pass through our sample, and our sample is going to absorb some of that light, so we'll end up with a lesser intensity that we can then measure with a light detector. That works out pretty simple. We can then define a percent transmittance or transmittance based on the amount that we see passing through our sample relative to the amount that we initially passed through. We're going to see that we have a nonlinear relationship between percent transmittance and concentration. So we're going to have our concentration and percent transmittance are inversely related, but they're also nonlinear, which means that that's not a very good way for us to calibrate what's going on in our sample. So instead, we have to define a term that's based on absorption rather than transmittance. Absorption we define as the negative log of transmittance, or the negative log of the light that actually passes through a sample versus the incident light that hits the sample in the first place. When we measure absorbance versus concentration as opposed to transmittance versus concentration, now we can see that there's actually a linear relationship in many cases. We can look at the slope of that. The slope of that line is going to be in the form y equals mx plus b, and we can actually change that so that the y is absorbance and the c, or the x is c for concentration. That makes a lot of sense. Our y is going to be obviously absorbance, that's on the y-axis, our concentration be on the x-axis. We can actually define that m as well. That m is going to be a factor of two different things. The things that are a factor of m are epsilon, which is a molar absorptivity, so it's essentially how much any given substance will absorb at a certain wavelength, and an L, which is how long that sample is, so how far the light has to travel through a sample of that concentration. And then of course the concentration is the X. Almost always we describe our molar absorptivities with units of absorbance, or the unitless, absorbance is unitless, but we give it on a per centimeter basis, so that when we have 1 centimeter cells, which is kind of standard for length, those will cancel out, and then we'll end up with just our concentration. So generally when we actually apply spectroscopy, since we do have molar absorptivities that are based on a single wavelength, we're going to add in a little bit more complication to our actual unit. We're going to have a light source, we're going to have a monochromator, which essentially is this meaning one color. It's going to divide our wavelengths so that we only see a few wavelengths at a time. And then we're going to have two different possible setups for our instruments. One might be a single beam setup, in which case we'd go just through the sample into the light detector like we had before. One might be a double beam setup where we alternate between two different samples, and each of those samples will pass to the same light detector. We'll measure them alternately. Usually we'd put a blank in one sample and then a sample in the other one so we can constantly blank out. Those are the most accurate instruments. A few other definitions for actually taking spectrum. Cuvettes are the things that hold our samples. We have single beam versus double beam. Single beam would just be passing through the one sample. Double beam would be passing through the two samples. We'd have to split the beam of light to do that. We also talk about the lambda max, or the wavelength max. That's the wavelength where the absorbance is highest. That's generally the one that we'll use to define our molar absorptivity and actually use to determine concentrations. That relationship, absorbance equals epsilon length concentration, is called Beer's law, but sometimes Beer's law will actually fail. One place where it fails is if we have polychromatic light. If we have too many wavelengths of light present, then we might end up with nonlinear responses. That's why we generally will introduce a monochromator into our spectrophotometer. We also will have failures if our concentrations are too high. Remember that we're actually measuring transmitted light, and the higher the absorbance goes, the higher the concentration goes, the higher the absorbance goes. The higher that goes, the less light we'll see, and the harder it is to generate any signal. So if we have concentrations that are greater than 0.01 molar, we'll sometimes start to see deviations from linearity. We'll also have problems with linearity if the concentration-dependent equilibrium exists and two species absorb light differently. So that's like if we have an acid and a base that are equilibrating, the protonated species absorbs one wavelength of light, the deprotonated absorbs differently. That's true of a lot of our indicators for acids and bases, and so that's a pretty common problem. Our best absorbance range is going to be from in the low absorbances, maybe 0.05 or 0.03 up to 1.0. Depending on the strength of the instrument, sometimes we can extend this a little bit higher, but we're going to be most likely to get linear data in that range. Now, we're going to end up having a lot of noise if we go too little light, and we're going to end up with a lot of error if we have too much light absorbed. If we look at a given spectrum, we'll be able to see a little bit more clearly some of these factors. We should be able to identify a wavelength max, a lambda max right here. So this is our lambda max. We also will see that there are a lot of other wavelengths that will also absorb. Generally, we'll have different absorbances at different wavelengths, which is why polychromatic light is a problem. We'll generally choose to calibrate only at the lambda max, and then we'll only look at that wavelength, because that will be very helpful for us. Notice that there are multiple relative maximums. Sometimes if we have other things that might also absorb near our lambda max, we'll choose a different lambda that also is the peak in order to determine these concentrations.